Okay, so in the next part of this chapter, part 3, we're going to start off by talking about sources of proteins. So we mentioned this before earlier in a previous video. Proteins and what they're made of, amino acids, are supplied by our diet. They're also supplied by recycling and the reuse of amino acids that are released during the breakdown of body proteins. So your body is, your cells are very efficient. They don't like to waste things. And so if proteins, like an enzyme, for example, is kind of old and worn out, instead of just like tossing it into waste, your cells will actually break down that protein and utilize those amino acids. They would go back into the amino acid pool, inside of that cell. Okay. However, some protein is lost, right? And so dietary protein is required to replenish and maintain an adequate pool of amino acids, especially those essential amino acids. Okay. Typical North American diet, so this is true for the US and Canada, about 70% of our proteins in our diet come from meat, poultry, fish, milk, cheese, legumes, and nuts. Okay. Heavily on the meat, poultry, dairy side of things. Worldwide, 35% of protein comes from animal sources, and the rest is going to come from protein sources. So we're a little bit, off skewed from the rest of the world. Our diets, again, tend to be richer in animal sources of protein compared to the rest of the world. Okay. So this is protein requirements. So protein requirements are going to vary by age and by sex. We already know that. So adult women, our recommended daily allowance is a little bit less than the RDA for adult men. Okay. Sources of protein are shown here. So tofu, this is a soy-based product. So this is a plant protein. It's a complete protein as well. Chicken breast, tuna, legumes would include beans like navy beans and kidney beans and black beans, nuts like almonds, peanut butter, eggs, cheese. It's high in protein, yogurt, milk, so on and so forth. Okay. So let's talk about plants. So yeah, plants are a source of protein. Again, many plant proteins are incomplete proteins, not including quinoa, soy, and buckwheat. Those are examples of complete proteins. So again, that difference is an incomplete protein does not have all 9 essential amino acids in adequate amounts, where a complete protein does. Okay. However, we can do mutual supplementation, right? We can do complementary foods to make sure that we get all 9 essential amino acids. So there is a way to have a diet pretty rich in plants and still get the protein that we need. What else? How else would we benefit from consuming plants as a protein source? We've talked about this, right, in previous chapters. Plants provide carbohydrates like fiber. They also provide vitamins, minerals, and phytochemicals. They also do not contain cholesterol, and they have little to no saturated fats. So again, a really good choice, for proteins. Because of this, they have been shown to decrease the risk of cardiovascular disease, certain types of cancers, obesity, type 2 diabetes. Okay. Sample menu for proteins. If we take a look here, we have this split between a 1,600 calorie per day diet and a 2,000 calorie per day diet. You can see serving size as well as how much protein you're getting per gram. Here's the menu. So if we started off with breakfast, we had low-fat granola. Low-fat granola has, in a serving size, 5 grams of protein. That's pretty good. Blueberries, and then a cup of fat-free milk. Again, same thing. Pretty good amount of protein. Okay, 8.5 grams. For lunch, Really great protein source, a lean meat. So this is grilled chicken breast. That's going to provide for 3 ounces, 25 grams of protein. For 4 ounces, 33 grams of protein. Salad greens will have some protein as well. Fat-free skim milk. Again, we're back up to 8.5 grams of protein. And then for dinner, again, high protein sources here, clams and mussels. Shrimp also provide protein. And then we've got some vegetables and some rice. Okay, snack, whole grain crackers, cottage cheese is a great source of protein, 7.5 grams. So total here, if we're looking at protein, you can hit 100 grams of protein in a day if you're doing a 1,600 calorie per day diet. And the same thing if you're doing 2,000, you can hit 131 grams of protein today. So we will talk about how to calculate how much protein one needs in a day. And again, this is a sample menu showing you that, you can get 131 grams of protein, relatively easily. Some individuals have a hard time meeting their required protein intake. Most people in North America, there's not a shortage of high protein foods. But for individuals who, don't like meat, they're vegetarians. It can be a little bit tricky meeting protein needs. And so supplementation may have to happen. We'll talk about that towards the end of the chapter. But, protein supplements, protein shakes, things like that. Okay, so again, we'll come back to that. Okay. So good sources of proteins. We talked about plants, right? And so plants can provide some protein, but you can see that meats, chicken, poultry, eggs, they do provide higher levels of protein per serving. Okay, so meats, dairy products, again, soy products, tofu, legumes, whole grains, quinoa, nuts, all really good sources of protein. Okay. So interestingly, when we talk about protein sources, in different parts of the world, individuals eat high protein foods that in North America we wouldn't think about eating. So this is called entomophagy. This is the consumption of insects. And this is something that in the future we may have to think about for global food security reasons. Also to when we think about our environmental footprint and decreasing our carbon footprint, decreasing water consumption, decreasing use of fertilizers, raising cattle takes up, a lot of energy, water, grain. It's much easier to raise insects. They have, again, a smaller need for food, water, space, energy. Okay. So again, worldwide, there are people in the world, communities that do eat bugs. And that might be something in the future that we start to see. Okay. So for example, crickets are pretty high in protein, grasshoppers, they taste like shrimp. Be sure to cook well. But look, so they're providing 30 grams of protein. I don't know about the serving size here, but mealworms, silkworms, crickets, termites, locusts, caterpillars. We may see this in the future. They're pretty versatile, right? You can cook these and just eat them, or they can be ground up and made into flours. So flour to use to make, breads and things like that. So they're pretty versatile. Again, in the future, we may start to see this more. Okay. Evaluation of protein quality. So we know about different sources, what makes one source better than another. Okay. And this isn't just based on the grams of protein that are provided, but different sources of protein have different quality. Okay. So protein quality, this is a measure that indicates a food's protein's ability to support growth and maintenance in humans, okay? It refers to how well this protein that we're consuming in our food, so dietary protein, provides the essential amino acids that the human body needs and how efficiently the human body can digest these proteins and absorb these amino acids. Not all proteins are created equal. Animal proteins tend to score higher. They tend to have a higher protein quality score, while many plant proteins tend to be limited in one or more essential amino acids, right? So we've already kind of established that. Okay, so let's talk about the measures involved here. So first of all, again, digestibility and bioavailability. So how much of this dietary protein that we're ingesting actually gets digested and how much of it actually gets absorbed. Okay, so this first measure here, digestibility and bioavailability, so how much of it gets broken down, how much of it gets absorbed, it tends to be much higher for plant proteins. So plant proteins tend to be digested and absorbed at a relatively high amount, so between 90 and 99%, where plant proteins are a little bit lower, 70 to 90%, okay? The second measure here, amino acid composition. So again, proteins are made up of 20 amino acids, 9 of which are essential, must come from diet. When we do amino acid composition, we compare the protein that we're in question with a reference protein that provides essential amino acids in amounts needed to support growth. So it's this comparison. The protein in question compared to a protein that we know does a good job, has a high quality. When this is done, getting the high quality standard there, that's going to be all proteins that provide all 9 essential amino acids in sufficient amounts. So those are going to be complete proteins. And then we have heard low quality proteins, right? Do not. They have at least 1 or more amino acids that are in limited amounts. Those are called limiting amino acids. Again, those are going to be those essential amino acids that are present in the lowest amount, and that tends to reduce protein quality. Okay, so the lower the number or relative amounts of these 9 essential amino acids, the lower the score becomes. Okay, so again, protein quality is based on how well the protein is digested and absorbed, and also looking at the amino acid composition of the dietary protein. Does it have 9 all essential amino acids in the proper amounts, in adequate amounts? Okay. So we've got some scores to talk about. So biological value, this is used less often. We'll talk about more commonly used scores as well, but just to kind of let you know how this score is calculated. We use this score when individuals, for whatever reason, have limited intake of protein. And so it's really important to monitor the quality of the protein that those individuals are taking in because they're not able to get high amounts of protein. So, for example, somebody who has kidney problems, they're going to have a limited amount of protein that they can take in. So every little bit of protein that they ingest needs to be high quality protein. All of it matters, right? Somebody who's, healthy and is not thinking about limiting their amount of protein intake, they're not thinking about this. Okay, so again, this comes into play sometimes clinically. Okay, only when the amount of protein has to be limited for whatever reason. So biological value, we use BV to represent this calculation. This is a measurement of how efficiently the absorbed food protein is converted into body tissue. Okay, so is it absorbed? Does it get converted? We determine this by comparing nitrogen. Remember, protein is high in nitrogen, right, from that amino group, right? So that's what we're going to measure, nitrogen. We're going to compare the nitrogen retention in the body, how much is kept in the body, with that was found in the original food protein. The more nitrogen that's retained in the body, that means that the food, if we look at the dietary protein, that amino acid composition closely matches the amino acid pattern found inside the body. So when you're eating proteins that are a good match to what you need to make proteins in the body, that's going to be a better protein. So the better the match, the higher the biological value. Okay? If the protein does not correctly match the body composition's proteins, then nitrogen will be excreted. Okay, so it'll be lost from the body in urine. Okay, so nitrogen gets excreted if the food, the dietary protein, and our body protein amino acid compositions do not match so well. So low match equals low biological value. The scale for biological value is a range from 0 to 10. Animal proteins, right? We're animals. So if we compare our proteins inside of our body to chickens, meat, beef, poultry, so turkey or chicken, we have a better match than we do with plants. Okay? Our proteins are more similar, if not the same, as those that are found in other animals. Okay, so most animal proteins have a pretty high biological value. So for example, eggs have a value of 100, it's the highest. Whey protein has a biological value of 100. Okay, so high quality proteins. Most plant proteins don't have a complete match with us. And so they're going to have a lower biological value. So for example, peanuts, which are still a great source of protein, they have a biological value of 50. So again, if I have to limit and really watch my intake of protein, I'm going to want the highest quality, so the highest biological value, because I have to limit my protein. Okay, but if I'm an individual who's not clinically doesn't have to limit my protein, then I'm going to get protein from a variety of different sources. Okay, peanuts are a great source of protein, but again, if I'm limiting my amount, I'm going to want proteins that match my amino acid composition. That's going to give me the most bang for my buck. Okay. Okay. There is another way, a couple we'll talk about here, to measure protein quality. And this second one is called the protein efficiency ratio, or PER, okay, PER. This calculation compares the amount of weight gain of a laboratory animal, so usually a mouse, okay, consuming a specific protein, the one that's being studied, against the weight gain of a laboratory animal that consumes some type of a reference protein. And usually the reference protein used is a dairy protein called casein, okay? This reflects biological value. So the higher the biological value, the higher the match of amino acids, the higher the protein efficiency ratio, okay? What that says is that the animal being studied here, again, usually a mouse, its amino acid composition, it's an animal, right? And so if the mouse is fed animal proteins, those animal proteins will most likely match the amino acid composition of proteins within the mouse. And so that's going to have a higher PER, also a higher biological value. That makes sense. Where plant proteins, again, are not going to be a perfect match. And so will they provide amino acids? Sure. But probably not the same pool that's going to be required by that animal. So that those would provide a lower biological value and therefore a lower protein efficiency ratio. Okay. The mouse is going to be able to use proteins that match the amino acid composition of their proteins a little bit better, which again is going to cause gaining of weight, muscle, and maybe other things as well. When do we use this? So the FDA uses this, the Food and Drug Administration, so the FDA is going to use this in specific instances, so to set standards for labeling of foods intended for infants. Okay, so again, a very specific way that this measurement is used. Okay, chemical score. Here's the next one, and we're going to use this in the next one as well. So chemical score is also known as the amino acid score, And what this score does is it compares essential amino acid composition of the dietary protein being tested to the ideal amount for the amino acids of a reference protein. And usually what's used here are eggs, okay? High biological value, high per value, also a high chemical score, okay? So again, we take whatever food we're looking at and we compare that food to a reference protein, you know, egg whites, egg proteins. And again, we're looking at essential amino acid composition, okay? Egg whites have a high essential amino acid composition, right? A high biological value, it's 100. And so if I'm comparing other animal proteins to this reference protein, it's probably going to have a high chemical score. But if I'm looking at maybe plant proteins, they're going to have a lower chemical score. Okay. And again, we've seen this term already, but the amino acid, the essential amino acid that is in the lowest amount is going to be called the limiting amino acid. And that limiting amino acid will determine the chemical score. Just to take this a step further, if we have a protein, let's say, for example, a plant protein that's lacking in one amino acid. Okay, so for example, if I'm looking at grains like wheat or rice, we looked at some of these in the very beginning of the chapter. I don't expect you to memorize this, but if we think back, we said if we paired rice and beans, we ended up with a complete protein. If we just look at rice, rice does not have lysine. And so lysine would be the limiting amino acid. And its chemical score would actually be 0 because it totally lacks that amino acid. Okay, so chemical score, again, is going to compare whatever protein we're looking at to a reference protein. Okay, and the last score, the last value here, this is called Protein Digestibility Corrected Amino Acid Score, PDCAAS. Okay, this is the most widely used method for determining protein quality. What we do here is it's calculated by taking the food's chemical score, which we just talked about in the previous slide, so the amino acid score, and multiplying it by its digestibility. If a protein, again, is missing one of the 9 essential amino acids, this score is going to be 0 because that's what the chemical score is going to be. The highest score is 1. Okay, so foods like proteins like soy protein, most animal proteins, they get a score of 1, right? They have all 9 essential amino acids, and oftentimes are highly digestible. Okay, however, peanuts, they have limiting amino acids, and so they're going to have a lower score. Okay, so these are all related, right? Biological value, per, chemical score, and PDCAAS. But again, they're kind of used for different things. This one is the most comprehensive. So PDCAAS is the most widely method used to determine protein quality. And that is the end of this part of the chapter.